Hello, dear students. Welcome to the channel and very much welcome back to the playlist in which we are discussing about the transmission line modeling and performance. Up until now, we have seen about the basics of transmission line, different types of transmission lines. We have seen short transmission line, medium transmission lines. We have also seen long transmission lines. We have seen the equations for voltage regulation and efficiency for each lines. We have seen phasor diagrams for all those lines, and we have also seen the derivation of generalized constants, or you can call them ABCD parameters for all three types of lines. In medium transmission line, we have seen two representation methods called nominal T and nominal pi representation. And for long transmission lines, we have seen a method uh, which is called a rigorous method. And today, in continuation to that, we are going to discuss about the tuned power lines. So, uh, today's lecture is going to be the continuation lecture of the previous lecture. So, if you haven't seen the previous lecture, link will be flashing on the top right hand side corner of the screen, so please go and check it out. And if you have already seen it, so let's get started without further ado. So in the previous lecture, we have understood the characteristics of long transmission line, and we have also seen we have also derived the generalized constants for the long transmission lines, right? ABCD parameters. So and after that, after derivation of my ABCD parameters for long transmission line, we have also seen uh, two different type of waves, incident wave and reflected wave. And we have done this interpretation of equation for long transmission line. In that, we have saw this, that gamma is equals to alpha plus j beta, which is nothing but multiplication of zy and under root of them. So, and we also derived the ABCD parameters here, see, right? So in continuation to that, let's come to this tuned power lines equation. So now, when we neglect the shunt conductance, we represent it by G, and the resistance, the line resistance, which we indicate by R. We can write, instead of Y and Z, J omega under root of LC. So gamma, which was actually the square root of the product of y and z, can be written as j omega into under root of LC when we are neglecting the shunt conductance and the line resistance. So now, taking the cos of it, taking the cos h of my gamma, or rather, just simply coming back here, what we did here. Uh, Okay, I didn't mention it on the PPT here, but we did it in lecture. Okay, no issue. Considering cos h into gamma L here, what will happen? Instead of this under root of yz, we can write j omega under root LC. So we can write cos h j omega L. L will stay as it is, and gamma's value we will substitute here. So we'll have cos h j omega L into under root LC. Okay. And same ways, if I want to consider the same thing for this sine gamma L, I can write this way: sine j h omega L, sine h omega L under root LC, right? So now, uh, come here and see, for the long transmission line, when we derived the ABCD constants, see, what was the value of A and D? It was cos h under root of yz. B was under root of z by y, sin h under root yz. And C was under root y by z, sin h under root yz. So we already knew how we substituted value of capital YZ to small yz in previous lecture, and today we are what we are going to do, we are continuing that. So now we already know what are the values. So when we substitute that in that matrix, so these are nothing but my ABCD parameters A, B, C, and D. To verify that, you can take these two values, the value of A and value of D, both are equal, and you can also do AD minus BC and you will get the value 1. So by doing that you can verify it. So we can write it like that: cos h omega l under root LC, it will be my A and D. The B will be JZC sine omega l under root of L by C, that will be my B, and the value of C will be J divided by ZC sine omega under root LC. Okay, so we did nothing but derived the ABCD. We just took the ABCD parameters and presented it in a little different way, right? And now we call this line a tuned line. And why? So let's come to that. Now see, if omega under root L by C will have to be pi n or n pi, what will happen here? Put this omega r into under root LC is equals to n into pi. And n can be any integer value, 1, 2, 3, up to uh, as far as you want to go. So when we do that, what will happen? It will go like cos pi, cos 2 pi, cos 3 pi, and it will go for B, it will go JZC sine pi, sine 2 pi, sine 3 pi, right? So ultimately, what we will get for the value of Vs, we will have this uh, cos pi, and whenever we consider cos pi, what is the value of cos pi? It is always 1, right? What is the value of cos pi? Cos 0. Uh, cos 0 is 1. What is the value of cos 90? Cos 90 is 0, right? So whenever we go to that, we will get this term. My term A will be uh, it will be 1, right? Because cos 0 will be cos 0 or cos pi will be 1. So based on that, what we will get Vs is equals to Vr, and same ways we will get Is is equals to Ir, right? So what is happening here? What is happening here? That receiving end voltage and sending end voltage are equal. Receiving end current and sending end current are equal, which means there is no voltage drop on load, and there is no loss of current here, right? So if we have no voltage drop on load, we call such line a tuned power line, right? You can call it a tuned power line because there is no loss. You're not losing any power, right? So it is called tuned line. And uh, even though, however, we say that the line is a tuned line, because in all practical scenarios you will find a situation when there will some loss, no matter how fine you try to tune it, but there will always be some loss, and the value of output and input are not same for all the cases. So practically such lines do not exist, but if you can tune it real fine, then they can be very economical for the system, right? For our system. And for high frequency lines, we can adopt such lines, the higher frequency lines such as telephone lines, right? For such lines we can adapt it. Now coming to the next point that I wanted to discuss, that the power through the transmission line, and how do we see it? So first, let's say what we have seen before last section. We have seen performance equations of transmission line for all three, short, medium, and long. We have seen the performance equations for all three lines in the form of sending end and receiving end voltages and currents, right? uh, in the form of Vs and Is. If you remember, when we started the medium transmission line, I have shown the formula to you. uh, Let me show it to you again. Here, as you can see, the formula on the right hand side, this one, Vs is equals to AVR plus BIR, and Is is equals to CVR plus DIR, right? So this was the formula which we used to derive the generalized constants for all the lines, or we also call them ABCD parameters for all the lines. So we derived this ABCD parameters for all type of transmission lines with considering their sending end voltage and current values and receiving end voltage and current values. But uh, what happens in transmission system, and I'm pretty sure you might have observed this as well, that any loads which are connected to your transmission system are always expressed in the terms of power. They are always, you will find the unit of your equipment or your load will always be watt, right? If you are using some other equipment like UPS, then you will have kVAR, right? So at the end of the day, the equipment's rating or the rating of the load will always be in powers. We measure the load rating in power, right? Be it real power or reactive power, or in or apparent power, right? But we always measure it in terms of power. So it will be more convenient if we can express the performance equation of my transmission line in terms of power, right? Specifically, if we are uh, consider all type of power, like all active and reactive, so we can express it in terms of complex power, and it will be more convenient for us, right? It gets a little bit hectic when we represent your transmission line in terms of voltage and current, and then you when you have to go to the distribution side, you again have to switch towards the power. So the calculation gets more difficult and it gets hectic. So what we can do that, we can uh, represent my whole line in terms of power only as well. So that is exactly what we are trying to do here. So what we will do, see, here we are having a generating station. This is my sending in voltage Vs at some load angle delta, and this is my receiving and VR at angle 0. Remember, every single time for every single transmission line, when we have drawn the phasor diagram, we have we took VR as the reference. We took VR as reference. Okay, my reference vector was always VR, and compared to that, all other quantities have been drawn, be it the current, sending in current, receiving in current, or sending in voltage, right? So my sending in voltage is having is Vs, and it is having a load angle delta, and Vr is my receiving end voltage, and it is having 0 degree shift, or it is a reference vector. So for this line, the generalized constants can be written as you can see here. A will be A angle alpha, B will be B angle beta, C will be C angle gamma, and D will be D angle delta. And remember, the value of A and value of D is equal, right? Even though here we are representing our quantities in a polar form, but still the value of A will be always equal to value of D. Now for the complex power at receiving end, we can represent my constant power at receiving end as SR, and we can write it by the formula of VR into IR star. Now you already know value of VR, but what is this IR star, right? It is conjugate of your receiving end current. So how do we find it? So let's come to next slide and see it. So based on the ABCD parameters, the first value of derivation of ABCD parameters, the value of Vs, can't we write Vs is equals to AVR plus BIR, and in that formula let's make IR a subject. So what we will have, we will have Vs minus A into VR divided by B. Now you already know what is the value of Vs. Vs is nothing but Vs angle delta, which is my load angle. You know the value of A. We have mentioned the value of all the parameters in the beginning of the theory. So A is A into A angle alpha. So we will mention it A angle alpha, and VR is nothing but VR. There is no angle associated with it, or the angle associated with it is 0 because we are taking it as a reference vector. And in the denominator you will have B angle beta. So we did nothing new here. What we did, we just represented our system in a polar form here. So there is nothing new or no rocket science applied here. Now we will because if you remember the vector calculus class, what do we do when we are taking the when we are working in the uh, polar representation? When we have to add or subtract, or when we have to multiply or divide my angles, we simply either add or subtract the angles. So here what we are doing, see here, Vs, and we are taking B, we are separating B for all the numerators. So we will write Vs divided by B angle delta minus beta. See, delta is in numerator as you can see here, and beta was in denominator. So which angle which will be in the denominator will get subtracted from the angle which is in the numerator. So here you will have delta minus beta. Again for A, for the second term, you will have A divided by B into VR, because VR was already present in multiplication, and we will have alpha minus beta, right? Alpha was numerator and beta was in denominator. So we did nothing new here. Uh, we just separated the denominator for both the numerators, and then we have to find the conjugate IR star. So to find the value of conjugate, what we will do, we will we will take the conjugate, which means we will reverse the signs of my angles which are represented in polar form, right? So what I will do here, that Vs divided by B will remain as it was, and instead of delta minus beta, it will become beta minus delta. We reverse the signs of both of my angles. So delta was positive, it became negative. Beta was negative, it became positive. So what we will have, we will have beta minus delta. Then again, A divided by B into VR will remain as it was. And instead of alpha minus beta, we will have beta minus alpha here. So what we did, when we took conjugate, we reversed the signs of the angles, and by doing that we will find the conjugate of my quantity. What was the quantity here? It was receiving end current. Now what we will do, we will simply substitute the value of receiving end current in the equation of my sending end power. So the equation was VR into IR star. So VR we already know, and we will keep the VR as it is, and we'll substitute the value of IR star here, and by doing that we will get SR is equals to Vs VR divided by B angle beta minus delta minus A by B VR square, because we already had a VR and VR got multiplied with itself again. So VR square angle beta minus alpha, right? So that is my sending and apparent power. Now if I want to find the active component, or if I want to find the active power for same sorry, receiving end, yeah, if I want to find the active power of receiving end, what I will do, I will simply take the cosine component of the SR. right? So by simply taking the cosine component of receiving and apparent power, I will be able to find the receiving end real power or receiving end active power. So when we do that, what we will get PR is equals to VS VR divided by B. So the term which represent amplitude will remain the same. So VS VR by B will remain same, and angle beta minus delta will become cos beta minus delta. Again, for the second term, the term which is representing the amplitude will remain same. So A VR square divided by B will remain same, and angle beta minus alpha will become cos beta minus alpha. Same ways which we found, same ways which helped us find the receiving and real power will help us find the receiving and reactive power as well. So to find the receiving and reactive power, what we will do, instead of cosine component, we will take the sine component. So we will simply substitute cos with sine, and we will have the receiving and reactive power here. So again, I'm not mentioning the whole formula because you got the point. So I will move on, and let's try to find the power which we will be receiving will with when we take beta is equals to delta, which means the load angle. When we take the beta is equals to load angle, we will receive the maximum power. And how am I saying that? So for to know that, come to this equation, the equation of PR or the receiving and real power. So when the value of beta will be equal to delta, what does it means? Beta, if beta and delta are equal, that means the cosine angle will become 0. And what is the value of cos 0? If you remember, the value of cos 0 is 1, which means this term Vs Vr divided by B will remain the whole term, which means it will be multiplied with 1. And when the term will be multiplied with 1, that means we will have the maximum amount of power we can get, right? And also, not to mention, the other term will remain as it is, because here delta is not playing any role. So because delta is not playing any role, the term will remain as it is, and the value of the term will remain as it is as well. So we'll have A VR square divided by B, the amplitude part, into cos beta minus alpha, the same way as it was. So we are getting the maximum real power or maximum active power here. And what will happen with the reactive power? So come here and see. When we have beta is equals to delta, which means sine beta minus delta, so sine angle will become 0. And what is the value of sine 0? The value of sine 0 is 0, which means the whole term, the first term will be 0, and what we will left with will be minus a VR square divided by B sine beta minus alpha. So we will have minus a into VR square divided by B sine beta minus alpha, as you can see here. That will be my reactive power. Now this was the calculations for receiving end. Same ways we can find the active power, reactive power, and apparent power for my sending end as well. So to do that, this time we will take SS, which is sending end apparent power, which will be equal to Vs into Is star, and Is star is complex conjugate of sending end current here. Now again, considering the first equation of ABCD parameters, first equation which we use for the derivation of ABCD parameters, Vs is equals to AVR plus BIR, and in that formula make IR subject. What we will have Is minus CVR divided by D. Okay, sorry, no, we are taking the second formula of it as well. We are taking Is is equals to CVR plus IR into D, and from that we are making IR subject, and we will have Is minus C into VR divided by D. Now what we will do, we will substitute the value of IR in the first formula, in this formula, right? So what we will have, Vs is equals to A into VR plus B into what is the value of IR, Is minus C into VR divided by D. So we will substitute it here. And uh, if we do math and we take this d on the other side, in order to take this d on the other side we have to take the LCM here. So what we will get, d into vs is equals to a into vr into d plus b into is minus b into c into vr, right? Which means b and bc and ad both are having vr in common. So we can take vr separately as I did here, and we can put ad minus bc plus b into is. Now we all know what is the value of ad minus bc, right? Ad minus bc is always is equals to 1, so which means we will substitute 1 instead of ab minus bc, and we will have d into vs is equals to vr plus b into is. And in that formula, when we make vr subject, we will have vr is equals to d into vs minus b into is. Now in that in this formula, when we make is subject, what we will have, we will have d into vs minus vr divided by b. So that will be your sending end current. Now let's represent it in the polar form. So by representing it in the polar form, what we will have d angle delta, which we saw initially, that d is associated with angle delta, into vs angle delta, small delta here, minus vr angle 0 divided by b angle beta. So we did nothing but we represented the same equation in the polar form. Now we will do the same thing which we did while deriving the is for while deriving the ir star, which means while deriving for the current for receiving end. So this time while deriving the current for sending end, we will do the same. We will separate the denominator for each numerator. So we will get d into vs by b angle capital delta plus small delta minus beta minus vr by b angle negative beta. uh, Again, the angles, what where did it came from? So the angles of numerator are added together, and the angles which were in the denominator are subtracted from the angles which were present in the numerator. So from that you can see that is is equals to d vs b angle delta plus small delta, both of them were in the numerator, minus beta which was in the denominator. Okay, and the angle associated with vr was 0, which means 0 minus beta because b was in denominator, so we are having negative beta. Now taking complex conjugate of it, so what will happen again, what will happen, the angles which were the sign of the angles will get flipped. So we will have beta minus delta minus del, right? Because beta was negative, so it will become positive, and the other two angles, small delta and capital delta, were positive, so they will become negative. The amplitude part will remain as it is. And on the second term, when beta was negative, it will become positive as well. So that will become the value of my is star. And coming back to the first equation of sending and apparent power, ss was equals to vs is star. So what we will do again we will substitute the value of is star um, in the equation of ss. So we will get d by b vs square, because vs was already present there, and we are again multiplying it with itself. So we'll have vs square angle beta minus delta capital delta minus, we will have vs vr by b angle beta plus small delta, right? In the second term, uh, the angle associated with vs was delta, but here we are having the value of delta in negative, and the value of delta which vs came with was positive, so delta delta cut each other in the first term, and in the second term there is no delta associated, and it is in the numerator we are adding its value with beta. So that becomes your apparent power at sending end. And to find the to find the real power or active power at sending end, what we will do again, we will take the uh, cosine of the angle which we had in the calculation of apparent power at sending end. So what will happen here? So by taking cosine, the numerator part will remain as it is again, d into vs square divided by b. And instead of the whole angle beta minus delta, we will here have cosine of beta minus delta. And in the second term as well, the numerator and denominator, which means the amplitude part will again remain as it is, and we will have instead of the whole angle beta plus delta, we will have cosine of beta plus delta. So that will become the sending and real power, ps. And to find the reactive power of the sending end, same ways what we can do, we will take the sine component. Just like we took the cosine component, we can take the sine component. So what will happen here, we will have instead of the whole angle beta minus delta, we will have sinusoidal angle of beta minus delta. And instead of the whole angle beta plus small delta, we will have sinusoidal component of beta plus delta here. So that will become the reactive power of sending end. Now to find the maximum power, you have to consider that cos beta plus delta is equals to -1, and the angle beta plus delta should be 180 degrees. So what should happen here, in the equation of ps, the second term, the angle of the second term beta plus delta, it should be 180 degree. And when it will become 180 degree, what will happen, the value of it will become -1, which means this whole term will become positive because it was already negative. See, so it will become positive. And what we will have the first term as it is, and the plus vr vs divided by b. So maximum power will be d into vs square divided by b into cosine of beta minus capital delta plus vr vs divided by b. So that will become your maximum sending end power. So that's what we derived. And again, remember, in the transmission lines, the value of a and d will be same, which will be 1 angle 0. The value of b will be z impedance angle theta. And by taking that, we can represent it values of our pr, qr, ps and qs, values of sending and active and reactive power, and values of receiving and active and reactive power by the equations shown here. pr is equals to vr vs divided by z cosine of theta minus delta small delta minus vr square divided by z into cos theta. qr will be equal to vs vr divided by z sine delta minus small delta, sine theta minus small delta minus vr square divided by z sine theta. ps will be equal to vs square divided by z cos theta minus vs vr divided by z cos theta plus small delta. And qs will be vs square divided by z sine theta minus vs vr divided by z sine theta plus small delta. So this will be the main components, which means active and reactive components of sending and receiving and of your transmission line. Now in practical cases, normally the resistance of my transmission line is often very small compared to the reactance. So what do? We simply neglect them. And when we neglect them, we can take the impedance is equals to the reactance, which means z will be equal to x. And because z is equals to x, we can take theta is equals to 90 degree. And when we take the theta is equals to 90 degree, what will happen to the receiving and active and reactive power? Let's see, and let's come and see here. The amplitude again will remain as it is, vs into vr. Instead of z, we can write x, so we will substitute x here. Cos theta minus delta small delta. So the value of cos theta minus delta, theta's value is 90 degrees, which means cos 90 minus delta If you remember the trigonometry class, cos 90 minus delta will always become sine delta. So we represent we wrote sine delta minus vr squared by z cos theta, and value of theta is equals to 90, which means cos 90. The value of cos 90 is 0, so the second term will become 0 here. Now come to the qr, the reactive power of sending end. So vs vr by z can be written as xr, or z can be written as x. So vs vr divided by x sine theta minus delta. So same thing will happen here. Theta is equals to 90 degree, which means sine 90 minus delta, which means it is equals to cos delta. So we are having cos delta minus vr square by z, which means vr square by x into sine theta. The theta is 90 degrees, which means sine 90. Sine 90's value is 1. So we are not mentioning anything here. Now one more a little small thing to add here, that we know delta is a load angle or power angle, whatever you want to call it. So it is usually very small, right? The load angle is never too large, right? It is always favorable to keep the load angle small. So it is always close to the cos delta. It is always close to that the cosine of the delta will come to is equals to 1, right? So what do we do? Instead of this cos delta, we can write 1. So what will be my equation of qr? So qr will be equals to vs vr divided by x, this value is 1, minus vr square divided by x. So that will be the equation of receiving and reactive power, right? So we will wrap up here, and in the next class we will be seeing the circle diagram, which is a very interesting and very important topic for transmission line perspective. So please attend the next class as well. And if you have any doubts, any queries or questions, you feel free to mention them in the comment section below. If you have any feedback for me, any suggestion for me, everything is welcome. You can mention that into the comment section as well. I will be try to reply your queries and questions as soon as I can. And till then, goodbye and thank you for listening.